Yeah, so are there questions from last time? So last time we covered whatever is here. I think that's what we covered last time. Okay, so since I take it that you don't have any questions, so let's begin with the second lecture. Okay, so as I told you, so what I'll do is that for the rest of the course, at least the first part of the course, like, am I clearly audible to everyone, right?
Yes, sir.
Okay, fine.
Yes.
So for the rest of the lectures, what I'll do is that I'll keep that iPad example as a canonical example that we will, elaborate on, and we'll try to exemplify that particular setting. So to start with, so remember the question that we had. So the question that we had to do with the iPad, that I have an iPad that I've purchased on a particular date, and I want to know what's the state of the iPad 5 years down the line. And when I say I state, I'm interested in finding out whether the sound system works the same way as it does today, whether the glossiness of the screen remains the same as it is today, and so on and so forth. Okay? So, of course, to have a setting, we'll have to formalize matter. So, therefore, let's start with this setting. So, I consider uh, a system of, so let's say a classical system, because at the moment we'll deal with classical statistical
Sir, are
mechanics.
you presenting anything?
Oops, sorry, I should. Yeah, but it says it is being presented, right?
Yes, we can see your screen. Uh,
Huh. But not this, not the notes?
no, we can see your note. I can see your notes online,
Uh,
Okay.
but the
no,
offline students need to fix it, I think.
we
So yeah, because the broadcast has started. So I don't know. Maybe there's a problem at your end. Here I can see everything. Like,
Yes. Try pinning Shamik's presentation. So,
Yes, sir. I can also
yes,
see the presentation.
you
yes, the
can see
online people
the
can see.
you can see the blackboard. I mean, the one on which I'm writing.
Yes, sir.
Okay, fine, good. Okay,
But the student who are doing online, offline, they can't see, I guess.
okay. So that I don't know. So that they have to fix, because as far as Google Meet is concerned, like, my iPad is being broadcasted. So I guess whatever I
so we
write.
can see now.
Okay, fine. So maybe there is a lag. Okay, so we start with the classical system of n interacting particles. So, like, is there a lag between what I write and, when I write and when you see? Is there a time lag? Yes, no, maybe?
Sir, can you please do the landscape version of that?
Thank you, sir.
Okay. Classical system of n interacting particles in three dimensions. Yeah. So we are considering a classical system of n interacting particles. For example, this system is my iPad, and n is 10 to the 23. Okay. So let's just write it. N is of the order of 10 to the 23 or larger. It could be even larger than that. Okay. And so that is the number of particles. And second is I consider this system to be, the system is described by a system Hamiltonian So let's call it h, which is a function of all the generalized coordinates and generalized momenta. So let me just write it since we are in 3 dimensions. So in interacting particles, what I should say is that not really particles, I should say degrees of freedom, right? I hope you understand by now after your course on in classical mechanics that there is a difference, an important difference between particles and degrees of freedom. The difference is that the degrees of freedom are all independent of one another. While the particles need not be independent, they may have some constraints and so on. So therefore, the whole of classical mechanics, when you write, when you couch it in the language of Hamiltonian dynamics, it is written or expressed in terms of generalized coordinates. Okay? I hope you understand, right? You know the difference between particles and degrees of freedom, right?
Yes, sir.
Okay. So please do speak up, huh? Because otherwise, it's difficult to make out. Okay. So there are n degrees of freedom. So therefore, there would be 3n generalized coordinates, which would be q1, q2, dot up to qn, which I'm going to denote it as qi, this set, where I runs from 1 up to 3n. And similarly, there would be 3n generalized momenta. P1, P2 up to P, sorry, here there should be 3n, I'm sorry. 3n. 3n because for every degree of freedom you need 3 coordinates and 3 momenta because you are in 3 dimensions. So therefore you need a total of 3n generalized coordinates and a total of 3n generalized momenta. If you are in 2 dimension, of course the total would be 2n generalized coordinates and 2n generalized momenta. So okay, so this I'm going to denote by the set pi. And therefore, the system Hamiltonian is going to be a function of all the generalized coordinates and all the generalized momenta. And we are going to assume that the Hamiltonian does not have any explicit dependence on time. Okay? So the QIs and PIs, they will of course have dependence on time, and therefore H is an implicit function of time, but it's not an explicit function of time. Okay? And we are going to assume that the system is isolated. I'll tell you what does isolation mean. Probably you have already heard this term in classical mechanics. So system is isolated. So what it means is that the system is not the system is the iPad. The system is not interacting with anything like outside the iPad. Okay, so that means what will happen is that the total energy of the system, since it's an isolated system, the total energy of the system is going to be a constant of motion. Is a constant of motion. You know these things, right? You know these things, right? Hello?
Yes, sir.
Okay. Okay, fine. So then what I have is I have 3n generalized coordinates and 3n generalized momenta, and since the system is isolated, that is, if I think of my isolation does mean it just means the following, that I am not being able to interact with the iPad. That is, I'm not being able to write anything on the iPad or change the settings or play with the or send the message on WhatsApp and so on. So So the iPad is completely disconnected from like anything outside the iPad. So it's an isolated system. Okay, like obviously you would scream at once that my goodness, your iPad, like if you are unable to write on your iPad and send a message on WhatsApp, then what's the use of using an iPad? So I'll say that this is the starting point of statistical mechanics to consider an isolated system. And eventually, of course, we'll get to the situation when the system is not isolated. That is to say that the iPad is not disconnected from the outside world, and I am being able to write something and send messages and listen to songs on YouTube and so on and so forth. But this is the starting point because this is as it turns out, as it would turn out, this is the simplest setting in which to set up the framework of statistical mechanics. Like anything that you do after that, or beyond this framework, is going to be more complicated, and we'll get to those things. But let's start with this simple setting. So, now, what are the so these are the generalized coordinates and these are the generalized momenta. So suppose I start with a given set of values of the generalized coordinates and the generalized momenta. I'm like as of now, not telling you how to measure those generalized coordinates and generalized momenta. But let's say by some, coincidence, I'm able to find out the values of all the generalized momenta and the generalized coordinates at time 0. Okay. So these are the values at time t equal to 0. And the question is, what would be their values at time t? Well, that's quite easy to find out because I know how the generalized coordinates and momenta evolve as a function of time. They are given by the Hamilton equations. So I know that qi dot is equal to del h del pi, and pi dot is equal to minus del h del qi. So therefore, what I need to do is that these are first order differential equations in time. So I need to solve them with this one as the initial condition, and this would give me the values of qi's and pi's at any time t larger than 0. Okay. I don't even know, like this is a problem that we discussed last time, that in practice this is an impossible task. Okay, so we have to somehow circumvent this problem or bypass this problem. But in principle, we know what we have to do, namely that given a Hamiltonian system, given a Hamiltonian, I know how to evolve the values of the generalized coordinates and the generalized momenta, because what I need to do is to just solve the Hamilton equations of motion. Okay. So there is a nice way to, by the way, before I come to that, let me just mention that you must have studied this in classical mechanics, that suppose you ask, how does the Hamiltonian function evolve as a function of time? Why would the Hamiltonian evolve as a function of time? In general, it would evolve because QIs and PIs evolve as a function of time. So you know what would be the equation. So you get dH dt is equal to, uh, there would be a Poisson bracket of h with h, which would be 0 plus del h del t. But in our case, del h del t is equal to 0, and this just tells you that the total energy is a constant of motion. So it's also, right, that dH dt is equal to the Poisson bracket of h with h plus del h del t.
Yes, sir.
And this is just a simple, like, a one-line derivation. You just take the derivative with respect to time and then use the Hamilton equation. So there is a nice way to visualize this picture, and that brings us to the concept of a microstate and a macrostate. Okay? So let's just introduce the term microstate. As the name suggests, what is a microstate? A microstate is a microscopic specification of the system. I must tell you that when I write a sentence to describe or define a quantity, these are not God given definitions. Okay? You all, excepting for maybe one or two, you all have this tendency to mug up definitions. Because I see that when somebody asks you something, you typically, this is what I found during, the various Viva Voce examinations that I had organized or I had been a part of. I have seen that all of you, when asked about a particular quantity, you define it in, all of you give the same definition, exactly the same. Just as your answer scripts, no? That all your answer scripts are kind of self-similar. Very difficult to make out whose answer script is this, excepting for the handwriting, all the sentences, equations, are more or less the same. Okay, so similarly, the definitions also turn out to be the same. But please do remember the definition. I mean, there is no such thing as a God-given definition. See, so long as you are able to convey the message, so long as you are able to convey the meaning to the person who has asked you the question, whatever way, whichever way you have, defined the particular quantity is a valid way. There is no such thing as this is the definition given in such and such book, and therefore this has to be the only definition on earth. Okay, so this is a rather stupid way of thinking about things. There is no such thing. So what is a microstate? It's a microscopic specification of the system. That is, it is a complete specification. Okay, so something cannot, like, this is a specification that gives complete information about the system. You cannot conceive of something which is more complete than a microscopic specification. So what's a microstate? How do I give a microscopic specification of the iPad? What I need to tell you is I need to tell you the values of all the generalized coordinates and all the generalized momenta of the of the system. Okay, so what's a microstate? So this one. So microstate, let's say at time t, this is specified. This is specified. Oops, sorry. By giving the values, that is the numerical values of all the PIs and QIs constituting the system. So for example, if somebody tells me that now the time is 11:52 a.m., 19th of March 2021, so what's the microstate of this item? So what I should do is that I should tell that guy the values of all the generalized coordinates and all the generalized momenta constituting this item. Of course, in practice, we know this is not possible. I don't even have a way to measure them. But in principle, this is a well-defined quantity. So that's the microstate of a system. But in practice, as we just mentioned, specification of a microstate of a system is not a feasible task. So this is not a feasible task, not a feasible task, because if somebody gives me this iPad, how am I going to know the positions and coordinates, the values of the positions and coordinates of all the degrees of freedom constituting the system? Like, even if I use a microscope, of course, a microscope has a finite resolution, and therefore I would not have a way to find out the values of all the particles, all the degrees of freedom making up this iPad. So this is not a feasible task. But there's something which is very much a feasible task, and that brings us to the concept of macro state. So what's a macro state? So remember, a micro state, it's a microscopic specification of the system. Oops, sorry. Something. So a macro state would be a macroscopic specification of the system. Macroscopic specification of the system, and this is very much a feasible task of the system. So what's a macroscopic specification? Let's think of the iPad. What I need to tell you is what's the weight of the iPad? What's the screen size of the iPad? What's the volume of the iPad? What's the color of the iPad? Okay, so these are quantities. So more specifically, a macro state deals with quantities that are experimentally measurable. So these are experimentally measurable quantities. For example, when you buy an iPad or a mobile or something, so what you do is that you typically visit the website, and somewhere you would get the specification. Okay, that this one weighs so 500 grams, and the screen size is 13 inch, and this and that, the color is black, and so on and so forth. So a macro state, it is a macroscopic specification. That is, you don't need a microscope to find out the state of the system. It's a specification of the system that involves macro quantities, like quantities that refer to the system as a whole and not to individual particles making up the system. Yeah. So, for example, the system that we are considering at the moment, this 3n generalized coordinates and generalized momenta. So let's just understand the microstate and the macrostate of the system at hand. So a microstate would be microstate at time t. So that would be giving the values of all the generalized coordinates and all the generalized momenta. And macrostate at time t. So I may tell you what's the number of particles in the system, what's the volume of the system, what's the total energy of the system. As you can see in this particular example, not in general, in this particular example of an isolated system, all these are constants in it. Because this iPad is an isolated system at the moment, so all these are constants in. For the particular example of an isolated system that we are considering at the moment. Okay? So I hope the distinction between a microstate and a macrostate is clear to all of you, right?
Yes, sir.
Okay. So you may think of many other examples. Maybe for example, I see that some of you are assembled in the classroom. So you may say, well, it's a system. And how can I make it isolated? Can somebody tell me how can I make it isolated? What are the ways to make all of you, like those of you who are assembled in the class, how to make you isolated? Nowadays, of course, there's a very simple way to make all of us isolated. But can somebody tell me what's the current name for isolation?
Network cut.
Network cut.
Quarantine.
Sorry?
Quarantine.
Yeah, quarantine. Absolutely. So, quarantine is it's this is the modern synonym for isolation. Exactly. You see this isolation. See all these terminologies that you come across in physics. They are actually taken from society. Okay, it's not that the physicists derived or came up with this terminology by by having a WhatsApp chat with some god or godly person. Nothing of that sort. These terms were picked up from society. Indeed, quarantine, when somebody is quarantined, we use the word that he is isolated. Isolated means what? That he is not able to like communicate, he is not able to go out, he is being confined to a particular room and so on. Of course, it's not complete isolation because, once he has to eat and drink, so therefore, once in a while, somebody comes in and feeds him or her and gives him a bottle of water. So it's not complete isolation, but let's say a very good approximation of isolation. And in case I have to isolate all of you in the classroom that you all are assembled in, what I need to do is I need to, close the door and, for example, cut off the internet connection. And yeah, maybe, that's enough to ensure isolation. So let's say, I would not, of course, recommend such a thing to be done. But, but let's say for the sake of argument, we do such a we do have such a state that all of you are, confined to a particular room and the internet is cut off and the doors are closed and so on. So that's an isolated system. So what's the macro state of the system? So a macro state of the system, that is the classroom, would be, I need to tell you what's the total volume of the classroom, how many students are inside the classroom, what's the temperature of the classroom. Presumably the air condition would be on. And then I can tell you what's the temperature, at what temperature is the air condition running in the classroom and so on. So you understand that these quantities, what's the temperature of the room, what's the volume of the classroom, how many students are assembled in the classroom. These are macro quantities. They can be very easily measured in experiments. Okay? And what would be the micro state? I need to tell you the positions and momenta. Well, microstate specification can happen at various levels. Maybe you can say that, okay, you may give me the microstate specification at the level of human beings, that is on the scale of human beings. And then I may say, okay, this student is sitting on this particular chair and his velocity at the moment is 0 because he is, completely stationary, is not moving around and so on. Or I may ask for a microscopic specification at the level of, let's say, quarks or let's say atoms and molecules. And then, of course, I need to tell you, where the particles are, what are the positions of the particles and so on. So typically, a complete specification would mean the latter, namely that, what are the positions and coordinates, what are the positions and momenta of the particles making up all the students who are assembled in this particular room. And as you can understand, it is an impossible task. No experimentalist or theorist would ever be able to find out or measure with any precision the values of coordinates and momenta of all the particles making up all the students. It's an impossible task. But macrostate is it's quite a simple thing to measure and so on. So there's a nice geometrical way of representing a microstate of a system. And so that's the concept of a phase space or a gamma space. So let me just introduce this one. Phase space or gamma space. Can you just hold on for a minute? Just let me taking a phone call. So just to where to okay. Sorry, how to. So, Samvit, how do I mute myself? What do I have to do?
Mute. You go to, yes, you go to the Google Meet app and
No? Oh, maybe this one? No, not really.
no. You are, I think you are logged in, but there is some other screen that is open, no? To join some other meeting. So you close that screen and then.
Oh, maybe from here.
Yes. You see the
Just
button
one.
below, right?
Yeah, sorry. Your phone call. Okay. So let's just come to where we left. So that's a macro state and that's a micro state. And now the question is, what's a gamma space or a phase space? So there's a nice geometrical way of representing a micro state. So remember that we have 3n generalized coordinates qi and 3n generalized momenta pi, okay, where I runs from 1 up to 3n. So you may think of a, so you may think of a coordinate axis or a coordinate system, a coordinate system, coordinate
Sir,
system.
sir, you
Huh?
actually not sharing the screen.
Huh?
Probably you not sharing the screen.
I did
Yes.
not do anything.
Okay. Okay.
Uh, not sharing the screen. How come? Because here it says, oh, share screen. Oh, very strange because it automatically. Now it's fine.
Sir,
Now it's okay, right? ठीक है तो?
ठीक है ओके सर.
Okay, fine. Okay. So now we come to the concept of a phase space or a gamma space. So there are, as I mentioned, there are 3n generalized coordinates and 3n generalized momenta. So you can think of a coordinate system. For example, we are all familiar with the XYZ coordinate system or the R theta phi coordinate system. Okay. So similarly, you can think of a coordinate system whose axes are labeled by the generalized coordinates and momenta. So that means it's going to be, instead of a coordinate system with 3 axes, it's going to be a coordinate system with 6n axes. So this is the coordinate system. So the different axes, each axis refers to a particular, generalized coordinate or generalized momentum. For example, this is Q1, this is Q2, this is Q3, and so on up to Q3n. And similarly, there's P1 and there's P2, blah, 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 up to P3n. So it's a 6n dimensional coordinate system. Okay, 6n axis and hence a 6n dimensional coordinate system. So this coordinate system has a name. It's called gamma space. Okay? Or phase space. Why it is called the phase space or gamma space, I'll come to it in a minute. But I hope the definition is clear, right? So there are 6n numbers in your hand. So you can think of those 6n numbers as being represented in a 6n dimensional coordinate system, and that 6n dimensional coordinate system is what is known as a gamma space or a phase space. Okay, what is this thing that came up? No. Sorry, cancel. Good knows what is this one. Okay, fine. So therefore, in this 6n dimensional phase space, of course, I don't have a way to draw this 6n dimensional phase space. This is the gamma space. As you can readily appreciate, a microstate of the system is represented by a point, right? Because it's 6n dimensional, so this is a microstate of the system at a given time. Is this okay? Why it's a point? Because a microstate means you need to have a set of 6n numbers, and we'll have a 6n dimensional phase space, and therefore it becomes just a point in this very high dimensional 6n dimensional phase space. Is this okay?
Yes, sir.
Okay. Now what is going to happen is that, you see, this is the microstate of the system, let's say at time t. And that is to say that this microstate would have the, let's just write the other way around. Uh, a microstate of the system at time t, that means this would have the coordinates given by qit and pi, this whole set. And I know this QIs and PIs, they change as a function of time. How do they change as a function of time? Following the Hamilton equations of motion. So as the values of QIs and PIs change as a function of time, this microstate is going to move around. That is to say that this is the microstate at time t, and then let's say 2 minutes later the values of QIs and PIs change according to the Hamilton equations of motion. So this point moves to that point, let's say after 2 minutes later, and let's say after 5 minutes it's here and here and here and so on. So if I look at infinitesimal time interval, I can think of a trajectory in this phase space. Okay, so I'm starting from this point, and then this is the direction of evolution. So this is what is known as a phase space trajectory. Why it is called a phase space? Because well, in earlier days, people used to identify a microstate with a phase. Because you think of a pendulum, for example. What would be the microstate of a pendulum? A microstate of a pendulum would, of course, involve the value of theta, the angle that the pendulum, the beam of the pendulum, not the beam, what is it called? The stick of the pendulum makes with the vertical. So that's called the phase. So somehow, it has kind of continued to be there, that particular definition, and so therefore it's called a phase space. And this trajectory, it is called a phase space trajectory. And then there are certain basic properties of phase space trajectory. So let me just mention them one after the another. Phase space trajectories. First of all, suppose now I'm not drawing like any longer the coordinate axis, because it would be kind of like annoying to keep drawing those 6n dimensional phase space. So let's say this is one phase space trajectory. Now the question is, so can it do something like this? So can it intersect itself? That is, can it self-intersect? And the answer is no, it cannot self-intersect. Why? This has to do with the following fact that, how do the QIs and PIs evolve as a function of time? They evolve according to the Hamilton equations of motion. And the Hamilton equations of motion, let me just go back to the Hamilton equations of motion. These are the Hamilton equations of motion. They are first order equations in time. So this one and this one, they are first order equations in time. That is to say that if I tell you the values now of all the QIs and the PIs, the values at the next time instant are determined once and for all, because these are first order equations. Therefore, to solve them, you just need one initial condition. So therefore, suppose I tell you the values of QIs and PIs as at 12:13 p.m., that's the time now. At 12:14 p.m., you know for sure what are going to be the values of the generalized coordinates and the generalized momentum. That is to say that for every given state, the final state, that is the state at the next instant, is very well defined. Okay? And on the basis of that, it's quite easy to understand why a trajectory cannot self-intersect. Why? Because let me just zoom in onto this particular section. So what is happening here is that there is a trajectory that is coming and going. So let me just put the like arrow direction. So it is coming this in this direction, then going this way and going this way and going this way. Okay. So then so so this so this arrow direction is fine, right? What I've done is that I've just like followed the direction of evolution of the phase space trajectory, right? Is the direction fine? The way I've drawn the arrows, is this fine?
Fine, sir.
Okay. So then the problem is, suppose I choose this intersecting point. I choose this intersecting point to be my initial condition. Okay. Suppose I choose this one to be my initial condition. Then I know on the basis of the Hamilton equations that if I solve the Hamilton equations, there's going to be only one final state. But here, what do I see? I see two final states, that it can go either this way or this way, right? So there are two directions. From this point, I see that there are two arrow directions outside. So this is inconsistent with the basic nature of the Hamilton equations being first order in time. Therefore, a phase space trajectory can never self-intersect. Okay, it cannot come and self-intersect, because if it self-intersects, then at the intersecting point, at this intersecting point, it seems like there are two future paths, but that is not possible simply because the Hamilton equations are functions of time. The Hamilton equations are first order equations in time. Is this okay?
Okay, sir.
Now, can somebody tell me that, in our case, we have assumed a Hamiltonian that is not an explicit function of time. That's why the energy is a constant of motion. Now, I claim that if the Hamiltonian were a function of time, explicit function of time, then I could have definitely had self-intersection. Do you understand why? If you understand, well and good, but if you don't understand, we can, discuss it at some other point. Let me just quickly tell you. Suppose, till now we have been talking about a Hamiltonian that is not an explicit function of time. But if it were an explicit function of time, then self-intersection could have been okay, because, what is happening is that, suppose you come this way and this way and this, so you are coming this way, you are coming this way, you are coming this way, and by the time you arrive here, your Hamiltonian may have changed. It's now a different Hamiltonian, and therefore you go this way. That could have been okay. So this could have been okay if the Hamiltonian could have been okay if H is an explicit function of time. No, like, is this point okay? So whatever I just said. By
Yes, sir.
the way, can you give me an example of a Hamiltonian that's not an explicit function of time and a Hamiltonian that's an explicit function of time? Can you give me an example? So let's first tell me an example of a Hamiltonian that's not an explicit function of time.
Sir,
Tell
of
me.
a simple pendulum.
So tell me, you just tell me the expression. I don't know what a simple pendulum is. You tell me
Oh,
what is
okay.
the
Okay, the Hamiltonian will be p square by 2m plus half m omega square x square.
Okay, so that's not an explicit function of time. Now give me an example. So this is not an explicit function of time. Now give me an example of a Hamiltonian that's an explicit function of time.
So charged particle in electromagnetic field.
Suppose I stick to the simple harmonic oscillator. What would be an example of a Hamiltonian that's an explicit function of time? What would you have required to do?
To
because
make the Hamiltonian explicit function of time.
yes,
Oh.
Damped oscillation.
damped oscillation. Can you derive them from a Hamiltonian? Oh, that's very strange. Like any damping cannot be a Hamiltonian system, right? Because the total energy would not be constant. It's definitely not a Hamiltonian system. What would you need to do to make this Hamiltonian
Uh,
an explicit function?
Sir, we can try to change the gravitational field, like if it was in a lift or something like that, and the acceleration is changing.
No, tell me the expression. I want the expression. What would be the Hamiltonian if I want it to be an explicit function of time? What would be the Hamiltonian if I want it to be an explicit function of time?
Sir, if a bead is moving in a circular wire and the wire is rotating with
No,
in
no,
about,
simple harmonic oscillator. No, no bead and so on. See, the first one is an example of a simple harmonic oscillator, right? I mean, it's a system, a simple harmonic. So suppose I want to make it an explicit function of time. What do I need to do?
sir, if we replace the rod with the spring,
Okay, and then does it become an explicit function of time? How?
because length will change with time.
So what will be the Hamiltonian of the system?
That I have to actually derive.
Hello?
Yeah. What would be
Sir,
the Hamiltonian?
can we just add a potential term like a function of t?
I don't know. So you tell me. Yes, indeed. So what you can do is that, well, it's a simple harmonic motion, but you can make the particle a charged one, and then you can drive it with an electric field that's a function, right? That
Yes,
you
sir.
can, and then it becomes. So what would be the Hamiltonian? What is the Hamiltonian of a charged particle in a time-dependent electric field? Hmm? So by the time you tell me, then the world will come to an end. Huh? So this is an example of a Hamiltonian that's an explicit function of time, because what I'm doing is that I'm driving it with an electric field that's an explicit function of time, right? Y minus q e x sine omega t, because that's the potential energy, and if you take the derivative with respect to x, you get the force, which is QE. Okay, so this is an example of a Hamiltonian, which is an explicit function of time, right?
So Shamik,
Ah,
even the damped harmonic oscillator would be explicitly time dependent, right?
yeah,
Provided we
because
can write a damping term properly.
no, a damping. Okay, let's write down the equation of motion of a damped harmonic oscillator. Oh, sorry.
Sir, is it possible to mute the Physics Lab account? A lot of background noise is coming.
Mute. I think it is muted. It is muted at this end.
Yeah, physics lab I think is the online. Uh, Sorry, the offline account.
So
So the
यहाँ पर
offline
तो
students
only
have
it
to
is
mute.
muted, right? I don't see. I
Not
don't
you,
know.
not you. The offline students have to mute, I guess.
Ah, the students have to do it because I cannot
Yeah.
do it. I don't have an option to do it. RKM very physics. Whoever is there.
Yeah, there is some electronic noise coming from the classroom.
Yeah, yeah. So those of you who are assembled in the classroom, can one of you please volunteer to mute your this thing? Gmeet?
Yes, and when they want to ask you something, they can maybe unmute and ask.
Yeah. So they all seem to be just stationary, not doing anything. So I don't
Sir,
know
it
how
is
long.
mute only actually.
No, but I see that it's unmuted because as you speak, you are, like I'm
I
manually.
unmuted it now.
But here it is showing. So suppose you, no, you mute yourself for a minute. Let me just see. Suppose you mute yourself. Let me see. It's still showing. I don't know. It seems like there is an account Arcane Very Physics, which is not muted at the moment.
Sir, actually, the account means we have to unmute and mute then again from the laptop or what is that computer. But we are using this mic. If we can unmute and mute it and ask from here. I
Okay,
mean,
so long as you are able to hear, at least my, whatever I say, then it's fine. No, because somebody complained that there's a background noise that's kind of annoying and so on. So it's definitely not from my end.
Yeah,
Okay,
yeah. So,
so
so I think they are switching the mic on and off. So if they're keeping the mic switched off, then we don't hear the noise.
oh, I see.
Yeah.
So I let you figure out whatever. So let's come to this example because so Samvit, you mentioned about this damped harmonic oscillator. Damped,
Yes.
let's say I'm trying to be as adventurous as possible. So that's the equation of motion of a damped harmonic oscillator. No? The problem is that this term, this alpha x dot term, this term cannot be derived from an underlying Hamiltonian. Any damping term, can you derive? Just try to do it. Can you write them as a set of Hamilton equations? Okay. Suppose you take, first you take the undamped case. Let's say you take the undamped case. Undamped case would be what? X double dot plus omega square x is equal to 0. So that's quite easy to write down in terms of Hamilton equations because one equation would be q dot is equal to p, and by q dot what I mean is q is same as x. Huh? Q dot equal to p, and then p dot would be equal to minus omega square q, right? Right?
Yes, yes, yes.
But suppose you consider the damped case, which is, let's say, damped and undriven. It's not being driven by some external force. So then you have omega square x plus what is it, alpha x dot equal to 0. You cannot write them as a set of Hamilton equations. Because why? Because damping, what it does is that, see, this system, it doesn't have any explicit function of time. So you would want the total energy of the system to be a constant of motion. But this damping, what it does is that it takes away energy from the system. Why does damping appear? Damping appears because there's some friction. As the pendulum is oscillating in air, it has to fight against the ambient air molecules and whatever is there, the dust particles and so on, and in doing so, it loses its energy. The total energy is no longer a constant of motion, and therefore, you cannot write a damped system as a Hamiltonian system. Okay? Damping appears only much later. There is no provision to treat damped systems within classical mechanics. Damped system appears almost exclusively within the framework of statistical mechanics, because in classical mechanics, you don't have a way to introduce damping. Okay, so it's not a question of terminology. It's just that you don't have the tool.
So are you saying that this alpha x dot term that we have added to our
Yeah,
Newton's equation,
yeah.
it has no analogous form in
Yes,
the
absolutely.
that you can put into the Hamiltonian?
Yeah, absolutely. Damping cannot be accounted for. Let me put it this way: damping cannot be accounted for. You must have done this, right? I mean, the classical mechanics students. I mean, Sambit, yours has been some long time ago. But the you classical mechanics students, like those who are assembled in the class or giving this lecture, sorry, offline, you probably know, no, that frictional force forces, dissipative forces, these forces are never dealt with in classical mechanics, right? Cannot be accounted for in the Hamiltonian formula. Virtual work, you don't know this D'Alembert principle, all those things in the Hamiltonian. Like even if you don't remember, you may look it up. But let me not digress at this point. If you have an issue, you tell me later. So this is a Hamiltonian that's not an explicit function of time. This is a Hamiltonian which is an explicit function of time. And for this one, for this second one, you may very well have a phase space trajectory that's self-intersect. Why? Because the Hamiltonian itself is changing as a function of time. So by the time you go around this loop and you come to this point, the Hamiltonian itself has changed, and therefore you may as well go in a different direction. But for this one, the first one, for this one, such a kind of like trajectory is simply not allowed. Okay, fine.
Yes.
Okay. The question was asked by some. Okay, you also asked the question. So we understood what is meant by gamma space, and okay, we were summarizing the basic properties of the phase space trajectories. So one property is that the phase space trajectory cannot self-intersect if the Hamiltonian is independent of time. That is, it doesn't have an explicit time dependence. And in this course, we are going to more or less in the first part of the course, we are always going to deal with an isolated system. The Hamiltonian has got no explicit function of time, no explicit dependence on time, and therefore the phase space trajectories cannot self-intersect. So what are the possibilities left for the phase space trajectory? So what it can do is that it can just wander around, do like this, and then it can do like this, and so on. If such a thing can happen, let me just rub it off because it took up a lot of my space. So this is one possibility. A second possibility exists that it could be a periodic orbit. There's no problem because it doesn't violate anything. You may have an orbit that just goes round and round. That's perfectly fine. Sorry, I could not draw it in the proper manner. So this is a perfectly fine. There's no question of self-intersection. It just repeats itself. The whole of it repeats itself. You come back. It's the signature of a periodic system that you come back to your initial condition after a certain time interval, and therefore you retrace the path. Okay? So this is perfectly fine if the Hamiltonian is and it does not have an explicit function, explicit dependence on time. So then this one is a perfectly fine. So these are the only two possibilities that exist for a phase-space trajectory. So we have understood what is meant by a microstate of a system, what's meant by a macrostate of a system, and what's a phase space. So please do remember that phase space is a way to visualize the dynamics of the system. If somebody asks you, show me a phase space around, well, you would say that it just doesn't exist because we exist in a three-dimensional space, and such a six-dimensional phase space, it simply doesn't exist. It exists only in our mind. Okay, this is a way to visualize the system in a convenient manner, but then there is no way that you can measure or you can pinpoint to a space and say, look, this is the base state of the system. It's all in our mind. But it helps to visualize the system, especially when you deal with nonlinear dynamical systems. That's something that we are not going to discuss in this course. This phase space visualization of the dynamics is a very useful and important concept. So that's why we study here. The next thing that we come across is this concept of ensemble. So this is a French word. It is by no means ensemble. So please, for God's sake, don't refer to it as ensemble. This is not ensemble. This is ensemble. Okay. So you can think of this one as ensemble. Ensemble. Okay. So what's an ensemble? So let's try to understand this thing. This is also again a very simple concept that is typically presented in a super complicated manner in books, for I don't know what is the reason behind such a complication. So it's the following. So let's come back to the iPad example. So as I told you at the start of the class, that for the rest of this course, at least for the first part of this course, we are going to consider the iPad as a canonical statistical mechanical system, and it's a very it's a valid statistical mechanical system. It has all the right attributes of a statistical system, namely that it really consists of a large number of degrees of freedom, 10 to the 23 or more. Okay, that's one. And secondly, I know how to characterize the microstate of the system. I need to tell you the values of all the generalized coordinates and momentum. Macrostate would be the weight of the iPad, and the volume and the screen, the length of the length and height, and the width of the this thing, and so on. So what's an ensemble? So think of the iPad. Suppose I tell you the macro state of the system. Okay. So for example, we were saying, we were using the symbols NVE to specify the macro state of the system. NVE, number of particles, and what's the volume and what's the energy. Okay. So let's say for this iPad, I tell you, let's say I do some experiment and I find out what's the total number of particles in the system, what's the volume of the iPad, and what's the total energy of the particles constituting this iPad. And this iPad is isolated because we have decided to study an isolated system for the time being. Eventually, we will get to the point where we may deal with a non-isolated system. But at the moment, it's an isolated. Suppose I give you the values of N, V, and E. So that's the macro state. And I ask you, can you tell me the micro state of the system? Can you please tell me the micro state of the iPad at this very moment? Micro state of the iPad. Well, I should write I maybe. At this very moment. In principle, I'm not talking about practice. You may say, oh, I don't know how to measure the coordinates and velocities and so on. But let's say, in principle, like, is it possible to tell me the exact microstate of the system? So what I should do is the following. I should try to solve equations in the following form. Okay? So microstate means I need to tell you the values of all the coordinates and all the momenta. So that's the set that I need to specify the values of. And let's say, this is something that we discussed last time, that given a system, it is your duty to find out what's the correct Hamiltonian of the system. What do I mean by correct Hamiltonian? Well, God knows what it means to say that correct Hamiltonian. Well, you have to devise a way to model the system. I may say that, look, this iPad is a solid, and therefore, I may think of a solid as being made up of atoms which are connected to one another by springs, and these atoms are vibrating about their equilibrium position, and so on and so forth. So, therefore, it is my duty, or it is my responsibility to find out or identify or write down the Hamiltonian of the system. No theory on earth can suggest to me the Hamiltonian of a given system. I have to be clever enough. I have to, rely on my wisdom, my knowledge, my intelligence to find out the Hamiltonian of the system. And suppose I know the Hamiltonian. Okay. So then I have to solve it. So let's say this is the Hamiltonian of the iPad. So presumably there will be a kinetic energy term, C1 square by twice m, I goes from 1 to 3n, and then there will be a potential energy term. And let's say the potential energy is a function of the separation between the particles. Okay. So Qi minus Qj, that's the separation between the particles. And typically all the interactions that we know of in nature, they all depend on the interparticle separation. For example, the electrostatic interaction, the gravitational interaction, they all depend on the separation between the particles. So what I do is that I do a sum over all particles making up the system, and this is the interaction potential between two particles, between a pair of particles. And what I do, why I do this restriction I less than j, because I don't want to double count. Okay. And let's say I know what the form of V is and so on. So then what I need to do to find the microstate of the system is I need to solve an equation of the following sort. I know that what is given to me is the total energy of the system. I I know the value of E. I know V. I know N. Well, N I have already taken care of. So then what I need to do is I need to solve an equation of the following sort. That is to say, I can say, given E, solve the above equation to get the value of Qi's and Pi's. Right? This is what I should do, right? Mathematically speaking, because I know that the total energy of the system is E, 5 joules, and I want to know the microstate, therefore I have to solve this equation. The left hand side of this equation is known, E, the value of E is known, and therefore I must solve this equation to get the values of Pi's and Q's, and then I am done. I buy myself an ice cream and go home and watch a movie on YouTube. I have done my job. Is this okay? I mean, not the YouTube part, but this solving this equation, this part.
Yes.
But you see, this is an impossible task, not just from the point of view of solving this equation, but there is an there is an added complication, and let's say this complication is kind of quite easy to understand. Then if you have one equation and you have six n variables, you have one equation and six n unknowns, right? So therefore, you are never going to have a unique solution. You are going to have many, many solutions, all satisfying the same equation, right? In order to have a unique solution, what you need to have is the number of equations should be the same as the number of unknowns. This is something that we learned in, I don't know, we were taught this in plus 5, I think, simultaneous equations and so on. So, first of all, these equations, this one single equation, that's going to be a very nonlinear equation. So mathematically speaking, I don't even know how to solve this equation. That's one problem. Typically, it could be a nonlinear equation. It's not going to be a simple equation like p plus q plus, p plus q equal to e. So nothing of that sort. There would be quadratic terms, cubic terms, cross terms, and so on. That's one. But secondly, even more than that, I have one equation and I have six unknowns. So that's never going to work out in the sense that this one equation is never going to give me a unique set of solutions for Qis and Qs, right? So a unique solution, oh, sorry, a unique solution is just not possible mathematically, right? Is this okay?
Yes, sir.
So you may think of it like if these all these things they appear very daunting to you, you may think of the following example. Okay, it's a non-statistical example, but let me just tell you that suppose somebody tells you that okay, I have three unknowns x1, x2, x3, and you give me those values of x1, x2, x3 that add up to 5, and let's say x1, x2, x3 are let's say integers, okay, and they should add up to 5. That is, you have to solve an equation. 5 is equal to x1 plus x2 plus x. Well, there are many possibilities. I may have 1 plus 2, that's one possibility. I may have 5 0 0, or I may have 1 4 0, or 0 4 1. So there are many possibilities. So a single equation cannot give me a unique solution for such a large number of unknowns as 6 n. And think of how merciless had God been, has God been, that we have given an equation that contains as many as 6 n unknowns, and n is 10 to the 23, and Jesus, like 6 into 10 to the 23 unknowns, and just one equation. I mean, nothing can be worse than that. So therefore, there's a technical way of saying it. So you say that given a macro state, that is given values of n, v and e, there are a very large number of microstates that are consistent with the given macro state. Consistent meaning that they satisfy all the mathematical equalities. Consistent with the given macro state. So that is to say that given a macro state, meaning given values of NVE, there are many possibilities of PIs and QIs. Micro state meaning values of PIs and QIs. There are many possibilities for PIs and QIs, and they are all consistent. None of these PIs and QIs, these values, they violate anything. They are all consistent with the given. But I don't know which one for sure is the microstate of the iPad at this bed. There are many. Is this okay? It's a very simple fact, right? And come to think of it, it's like very simple thing, right?
Yes,
So
sir.
there's an experimental viewpoint on this. You may say that look, suppose I have this iPad, I find out the weight of this iPad, and let's say by some means the number of particles making up this iPad and the screen size and so on. Just on the basis of this information, can I tell you the generalized coordinates and momentum? Come on, I mean, like, are you mad or what? It's simply not possible. How can I do it? Because there are so many arrangements of coordinates and velocities which are possible. They would all be consistent. They would all be giving me the same iPad. But microscopically, they may be very different. Experimentally, you may say it this way, that this iPad Pro that I have, this the same batch of iPads, let's say the same, a product belonging to the same batch has been purchased by people around the world. They all have exactly the same version of iPad. So the macro properties are the same. They all have iPad Pro, 13-inch, and whatever. I mean, this operating system and so on. But microscopically, they may be very different. Right? So that's a way to say that there are many different microstates, all consistent with the given macrostate. So you have a very large number of microstates. So there's, like, I can put it this way, that there's a whole collection of microstates. There's a whole collection of microstates, all consistent And this word is very important, consistent. Consistent with the given macro. Consistent just means that it satisfies all the required mathematical equality. Consistent with the in a few minutes give you an example of an inconsistent microstate. But let's first understand this one. A collection of microstates all consistent with the given macrostate. Okay? So this is such a long sentence that you always tend to come up with a word or a phrase for that, and the word that is used for such a long sentence is ensemble. In fact, it's a French word that just means a collection. Whenever you have the word collection in English, you have the corresponding word ensemble in French. So what's an ensemble? An ensemble is a collection of microstates consistent with the given macrostate. That is, given a macrostate, all the microstates that I can write down or I can have in my mind, I can list down in my mind, all of which are consistent with the given macrostate. There's a name for it, and it's called ensemble. And let me take a question, but before that, let me give you an example of an inconsistent microstate. Okay? So let's come back to this example that this is the microstate NDE, and I'm asked to find the microstates which are consistent with the given macrostate. Suppose I build a microstate that has got, let's say the microstate is this one. So this is an example of an inconsistent microstate. Why? Because I have n degrees of freedom, but then I have, so P should run from P1, P2 up to P3n, but I have an extra P3n plus 1 here and an extra Q3n plus 1 here. So this is never going to satisfy the constraint. Okay, so this is an example of an inconsistent, stupidly inconsistent. I am given n degrees of freedom, and I have, I have constructed a microstate that contains 3n plus 1 parts. So that's like a stupid 3n plus 1 code. That's stupidly inconsistent. Okay, so that's an example of an inconsistent microstate. So tell me at this point, do you understand in very clear and precise terms the meanings of microstate, macrostate, phase space, and ensemble? These are the four concepts that we have dealt with up till now, and it is very important. These are kind of the pillars of statistical mechanics. So it's very important that it's very important that you understand them in clear terms. Tell me if you understand, and if you have a doubt, then please do tell me. And please, for God's sake, from now on, don't think of a statistical system as just my iPad. So that during the Viva, say if I ask you, give me an example of a statistical system, sir, your iPad.
Sir,
Uh,
sir, can you explain that ensembles that microstate that are consistent with the macrostate? What do you mean by that?
I told you, no? All microstates that satisfy the basic equation that the total energy should be E, the total volume should be V, and the total number of particles should be N. Okay? Let me give another example. Let's say this is my iPad and the macrostate is NDE. Okay? And I ask you, give me an example of a microstate. You say, well, yeah, okay, so that means I have to tell you the values of the positions and the momentum of the particles picking up the iPad, okay? And let's say I give you a value of Q1 which is outside the iPad. In principle, it is possible, right? But in practice, such a microstate cannot be consistent with this. So think of it this way. Okay, let me, maybe iPad is difficult for you to comprehend. Let me give you, let me come back to this class example. That your macrostate is the volume of the classroom, the number of students assembled in the classroom, and the temperature at which the air conditioner is running. On the basis of that, I tell you, okay, now you tell me the positions and coordinates of all the particles making up all the students and the chairs and the cables and this and that making up the classroom. Just give me give me the values of all the coordinates and all the velocities, right? That's the question, right?
Yes,
And
sir.
now in answer to that, you say, well, there is a particle which is sitting in Belur Math, and that's a microstate. Okay, so suppose you give me you give me a microstate in which the coordinate of one, let's say Q1 has a value which is Belur Math. I would say, well, that's a microstate for sure because you have given me the values, but that's an inconsistent microstate. Why? Because the macrostate has to do with the classroom and you have given me a value which is outside the classroom.
Okay, sir, I got it.
Okay? It's a very simple thing that you have to give me the values which satisfy the constraints. What are the constraints? That the total number of particles should be n. So you cannot construct a microstate that contains n plus 1 particles or 6n particles. It's not possible because I've told you that the total number of degrees of freedom is n. You cannot have n plus 1 particles. Okay? Or for example, suppose I've told you that the volume of the system is n. That means all the QIs would have to lie within this volume, right? All the atoms and molecules making up the students and the chairs and the tables, they have to lie within the classroom. You cannot have an atom and a atom or a particle or a molecule which is outside the classroom because that's not consistent. That's not part of your system. Okay? So similarly, I tell you that the total energy of the system is 5 joules, and you construct a microstate for which the total energy is minus 15 joules. Then I would say, Arey Baba, I told you no, the total energy is 5 joules. How can you have a microstate which is minus 15 joules and claim that it's consistent? It's definitely inconsistent. Right?
Sir,
Yeah,
hello.
yeah.
Sir, please explain the place where you said there are one equation and
Ah, this equation, no? I told you that the total energy is E. So you have to solve this equation to find the values of QIs and PIs, right?
sir, in uh, Hamiltonian equation there are six n equation,
Yeah,
but here you said the one equation.
yeah, because I told you that the total energy is E. So therefore, you have to solve by solving the Hamilton equations. How are you going to find the microstate? The Hamilton equations tell you how the microstate evolved in time. They don't tell you the values of the microstate, right? Hamilton equations are going to tell me how does the microstate evolve as a function of time, not the microstate itself, right?
Okay, sir.
See, you have to find the values of QIs and PIs, and once you know the values of QIs now, then you apply Hamilton equations to find the values at the next instant.
Sir,
Huh.
sir, in the description of a macrostate,
Huh.
we have already defined it in terms of NVE,
Huh.
and I want to ask you if it is possible to describe it in terms of the constraints rather than the number of particles.
Well, these are the constants. Total number of particles has to be equal to n at all instants. You mean
Okay.
constants in the in the sense that in classical mechanics the dynamical
Yes, yes, yes,
constants?
yes,
No,
yes,
it's
yes.
not possible because most of these dynamical constants cannot be experimentally measured.
Okay,
Macrosets do with quantities that have to be experimentally measurable. Because
okay,
ultimately, the aim of statistical mechanics is not to build a framework which is of little use in practice, but to build a framework that can be used to do something useful. Namely, as we go along, we will see that this macro state specification of a system has to do with quantities that you can measure in experiments, not some quantities quantities that you have no idea how to, for example, let's say you are working with, a central force. Then you have this constraint that, there's this vector that is conserved, this length vector, this Runge length vector or whatever, that has some properties. But you see, these are not really experimental quantities.
Yes, yes,
Macroscopic
yes.
meaning they refer to the system as a whole. So what I can tell you is, let's say I tell you the total energy of the system, the total number of particles, the total volume, the total kinetic energy, the total potential energy. Let's say what's the color of the iPad. Things that don't refer to individual particles, they refer to the system as a whole. When I say that the color of my iPad is black, it is of course a meaningless question to ask, is the color of second particle black or fifth particle black? I would say, well, the concept of whether a particle is black or white or green or red is just not defined. At the level of individual particles, you cannot talk of such quantities. But black, it's a color that can be, perceived by our senses, and it's an experimentally measurable quantity. Why? Because I can bring it in front of my eyes and I can find out whether it's black or, I mean, so long as I'm not colorblind. Well, black, I think, can be perceived by even a colorblind person. So that's fine, I guess. Okay, let's say red and green. I do the experiment. So macrostate has always to do with quantities that you can measure in experiments. And microstate has to do with quantities that unfortunately you cannot measure in experiments. If you could measure those microstates in experiments, that is finding out the values of QIs and PIs, then you are done. Then you go home. I mean, then there's no need to study statistical mechanics. But unfortunately, neither in statistical mechanics nor in quantum mechanics is it possible to find out the values of all the coordinates and all the momenta, not even at the mathematical level. Forget about experiment, not even at the mathematical level. Possible because, yeah, hello? Yeah, okay, fine. So somehow, at the mathematical level itself, it is simply not possible just because you have too less number of equations and too many variables. 6 into 10 to the power 23 unknowns, and you have only a few equations. If there are constants also, then also, it's impossible because you have too less number of constants.
Yes, sir. Got it.
Okay, good. Okay, so ensemble, and so what I would do is that, I mean, I'll make some more progress, but at the end of the class, like after the class gets over, what I would urge you to do is to think in your mind of examples that look, you come across, you look around, and the systems that you come across. You yourself is a very good statistical system because our bodies are made up of so many atoms and molecules and so on. But when somebody tells you this guy is, he would not specify the microstate. He would just say this guy has fair complexion and the height is 5 feet 4 inch and the weight is 65 kilograms and so on. He would not say, oh, the microstate, there is one atom at the moment sitting on the nose and so on. Okay, it's simply not possible. You just don't know how to do it, how to measure it experimentally. Okay, good. So this ensemble idea is, I guess, clear. Now we come to this space once more and find out how to represent an ensemble. So this is my gamma space or phase space, the 6n dimensional phase space. I told you one microstate is a point here, and an ensemble is a collection of microstates. So therefore, let's say at this instant, I somehow find out, I make a list of all possible microstates which are consistent with the given macrostate. That is to say that at this instant, I make up my ensemble. I have a way to, let's say, find out all the possible microstates. So each microstate would be represented by a point. So therefore, an ensemble will be represented by a collection of points, right? So a collection of points in phase space represents an ensemble. Okay, fine. Is this okay?
Yes, sir.
Okay. And remember that the number of microstates is going to be quite large, right? Because you won't have one unique solution, so there's going to be many solutions, and therefore there's going to be many mics. Just think of yourself. Now, suppose I tell you your height and your skin complexion and your body weight, then there are many possibilities for the atoms and the molecules for their positions and velocities. So there's going to be a huge number of microstates that's possible, and therefore this phase space is going to be covered up with a very dense collection of particles. Sorry, what did I do? Oh, sorry, ah, sorry, sorry about that. So this phase space is going to be filled up with a very dense collection of points at a given instant. Okay? Now the next question is, are these points, these individual points, are they going to be remain stationary in time? Let's say this is the picture at t equal to 0. At t equal to, let's say, 5, is the picture going to remain the same?
No, sir. At macroscopic details, it is no.
At the macroscopic level, it's going to remain the same, because I told you that I'm dealing with an isolated system. Therefore, the total energy is not going to change, the number of particles is not going to change, the volume is not going to change. But each of this microstate is going to trace out a trajectory, a phase space trajectory. Okay? So therefore, each point, you can think of each point is like a person, let's say. And these persons, I mean, they are not stationary in their position. They are going to move around. So therefore, if this is the, these are the these are the positions of the points at time t equal to 0. So at time t equal to t equal to 5, it would be something else. Let's say some points move out there and so on. So the points are going to move around. So therefore, this collection of particles, they would change their relative orientation, and therefore I would have a, suppose I have a camera. Well, nowadays we typically don't have a camera. We have a mobile camera. Suppose I take a snapshot, a snap of the points at time t equal to 0. I would have one picture. At time t equal to 5, suppose I click, I get a different picture, because the points, the microstates, are going to move around. That's okay.
Yes, sir.
Yes, sir.
Fine. And tell me one thing. So this thing, I will leave it to you as an exercise. It's a very simple thing, but I'll leave it to you as an exercise. Okay. Now we come to this concept that suppose, so forget about statistical mechanics for the moment. Like, I guess all of you have some experience of traveling by train. I guess most of you travel by, you commute by local trains, and at least all of you have had at least one chance to travel by train somewhere, in from some place to some other place in India. And suppose you go to a train station. So what you do is, suppose, so train station, if you look at the train station, let's say from like slightly above the ground level, let's say a cause grain view. Okay, suppose you are in a helicopter. You are one of those lucky political leaders, and you are getting a view of the scenario, and then you are in a helicopter, and you are viewing the train station from above. What do you see? You see that what you are going to see from above is that, oh, okay, sorry, I wanted to talk about train station. I ended up drawing phase space. So there's no phase space in train station. Sorry. So if you look at the train station from above, sitting in your helicopter, what you see is that, let's say this is the train station. You are looking at it from above. So what you see is that there are some regions in which there are many people which are assembled, and there are some regions which are where there are few people, and again there's some gathering here, and then less people here, and less people there, and so on. Right? So this is the kind of picture that you would see, right? You must have seen this. You don't have to go to a helicopter. Suppose you are standing in a flyover, or let's say like an overbridge, and you are getting a view of the train station. You see that there are some places where a lot of people have gathered together, have assembled together, and maybe a part of the station is kind of empty. Not many people are there. There's a vending machine, and some people have queued up there, and so on. So that's the picture that you get. So what's the first thing that comes to your mind if somebody asks you to characterize the system quantitatively, to characterize this picture quantitatively? What do you do? Can somebody tell me what is the first thing that you talk about? Like even colloquially, like even when you talk to each other, you know we don't talk to each other in, let's say, statistical physical terms. We use common terminology. So what's the first thing that you talk about? First word that you use. It's an English word. I don't know. Probably there's a corresponding Bengali word, but that I'm kind of unaware of. So, what's the first thing that you talk about? When you see that there are some regions which are very dense, and there are some regions which are kind of vacant, not too many people, in that region, and so on. What's the term that you talk about? I mean, you use.
Distribution?
No, you don't use. Do you use? My goodness, do you use the distribution when you talk to your friends? I'm standing in Howrah and I find the distribution of people. Come on, we don't use distribution. I think distribution word, and this as a word has caught up after like Corona. Everyone is talking about distribution. So God knows what is the distribution. We don't talk about distribution. At least I never talk about when I talk to my friend or my mother or something. I don't talk about distribution. We talk about something else, something more familiar to us, to everyone.
Gathering?
Something similar. See, a gathering, it really doesn't quantify the situation. We use another term. So the term that we use is density. We say it's very dense here. हाँ यहाँ पर बहुत भीड़ जमा है ना, बंगाली में से এখানে খুব भीड़ জমেছে, डेंसिटी এখানে यहाँ पर भीड़ जमा है, इसका मतलब है कि a lot of people have gathered together, so the density is very high here, low there. Density is the word that we use, right? We say that glycerin is very dense compared to water and so on. So density is a word that we often use, right? Density. Hmm? So
Yeah.
similarly, right? That's the thing that it's a, oh, it's so dense here, it's so, you say that, there is part of the train station, it's like densely populated. We say you use this word when talking about Calcutta, let's say. We say that the southern fringes of the Calcutta are not so densely populated, and indeed it is so, that it's not so populated. And we say, that region around Belur Math, it's very densely populated. Like everywhere you see people, maybe not now, maybe like at other times. I mean, now, like during this like Corona time, like the density has come down more or less everywhere. But usually we use this word density. So similarly, let's now come back to this phase point, that whenever I have a large number of points, and remember the number of microstates is huge, and as it would turn out, I kept on saying huge, huge, huge. I should give you an estimate of how huge it could be. And later on, we will do an exact derivation of this result. Can somebody tell me what is the number of microstates, consistent microstates? How large is that number? N is 10 to the 23. So what's the number of microstates that you think this should be the number of microstates of that order? Make a guess, make a wild guess.
Probably factorial of that number.
Roughly, I would say. Well, it's like even worse than that. But typically, the number of microstates is exponential in N. Number of microstates. How large is that, by the way? Let's make an estimate. E exponential, it's the fastest growing function, no? That as a function of x, e to the x, it grows like hell. E to the 2 is, let's say, e, suppose I take it to be, let's say, e is not 2 really, 2.78 dot dot dot, but let's say for like, for simplicity's sake, let's say e is equal to 2. So e to the 2 is 4, but e to the 10 is what? It's 10 to the 3. So when you go from 2 to 10, the number increased from 4 to 10 to the 3. E to the 10 is, so suppose you take e to the e to be equal to 2, then 2 to the 10 is 1024, which is like 1000. Right? So, when the exponent increases by, it becomes only 5 times, this number, the number itself, e to the 2 and e to the 10, this became 25 times larger. Right? So therefore, you can understand that e to the 10 to the 23 is going to be a number that's beyond our imagination. It's probably, it's like kind of to infinity, kind of. Of course, infinity, I mean, there's no definition of infinity. Infinity is anything, it cannot be quantified. That, this is infinity. Infinity is larger than like anything that we can perceive. Okay? So e to the 10 to the 23 is beyond our imagination. Is it million? No, it is larger than that. Billion? No, larger than that. Trillion? No, larger than that. It's like beyond our imagination. So you can understand that the number of consistent microstates is going to be something which cannot be stored on any reasonable computer. Such a huge number. And therefore, if you have such a huge number of microstates, then if you look at this, sorry, if you look at this, if you look at the phase space, then the phase space is going to look exactly like the picture here. That there will be some regions which would be densely populated and some regions which are sparsely populated and so on. Right? Maybe here the points are very close by, and maybe here there are not many points, and here also there is a dense region and so on. The best way to draw this picture is to use a chalk, right? And then you kind of make some shades, different shades, and the amount of shading that you do would correspond to the amount of, the density there. Unfortunately, with this pencil, I don't know how to shade, but whatever I did, I mean, I tried my best. So whenever you have such a thing, what you do is that you associate a density. Hmm? So we will also associate a similar quantity here, namely what is known as the phase space density. So let me just define this one. Phase space.
Sir, we can't hear you.
Samvit, you can hear me?
Yes, online. Uh,
So maybe it's a problem with
I
your.
can, yes.
So it's a problem with your internet connection, maybe. I don't know what to do. Can you hear me now?
Is she online or offline?
I don't know.
Okay.
No, they all seem to be online. I don't know. It looks like they're online. Are you online or offline? Okay, if they're offline, how can they answer this question? Okay. Can you hear me? Hello? Hello?
Sir, we can hear you, but don't know about her.
So can you please call up one of the students to find out if they can hear me and so on?
Okay,
Sir, we
sir.
can hear you now.
So it's a problem with the university internet connection, I guess. Because here everything is fine.
Shamik, you should also put your iPad on charge, I think.
But I'm almost done. So I have only,
Okay.
I would say, 10 minutes left. And so. Acha, let me not, start with this new concept because in 10 minutes it would not be done. Let me tell you the exercise that I want you to think about, okay? And you don't get a grade or some points for answering this question. If you can yourself answer this question individually, you try it yourself, and if you yourself can answer this question, then you can buy yourself an ice cream. Of course, I am not going to pay for it. So let me just not get to this thing. Let me just think of it. Sorry, tell you this exercise. It's the following. Let's come back to the phase space. And I told you that there are all these different microstates, consistent microstates. Okay, each point represents a microstate here. And this one is going to evolve according to Hamilton equation. This one is going to evolve according to Hamilton equation. This one is going to evolve according to Hamilton equations and so on. Question. Can the phase space trajectories corresponding to different microstates intersect each other. Is the question clear? Look, here in this figure, this one, let's say this is my microstate 1. So this is the path for microstate 1. And let's say which one is it intersecting? Low battery, close. So suppose there is a microstate 2 here, and then this is a point, and then there is a phase space trajectory coming out. This is the phase space trajectory for microstate 2. You see at this point there is an intersection. My question is such an intersection allowed or not? Can you have such an intersection? If yes, why you can have such an intersection? If no, why you can't have such an intersection? Please remember that previously what we had proved is that a given phase space trajectory cannot self-intersect. But now I am asking, I have two different phase space trajectories. One starting from this point, this microstate, this is doing this, and there's another one that is doing this. Can you have an intersection between two phase space trajectories originating from two different microstates or two different phase space points? That's the question. Is the question clear? If the answer is yes to this question, that there can be an intersection, then try to argue why there can be an intersection. If you feel that no, there ought not to be any intersection between two phase space trajectories, then try to rationalize as to why you can't have such an intersection. Is the question clear?
Yes, sir.
Okay.
Yes, sir.
So I guess I leave you with that. So just to recap, so today what we did was we started out with a Hamiltonian system that's isolated, and the Hamiltonian doesn't have an explicit dependence on time. We talked about the microstate of the system. What's a microstate? That's like telling you the values of all the coordinates and all the momenta of all the degrees of freedom making up the system. That's a microscopic specification of the system. Then we talked about macrostate. Macrostate has to do with specifying values of experimentally measurable quantities. Quantities that refer to the system as a whole and not to individual particles. Then we talked about phase space. That is, it's a 6n dimensional, 6n because you are in 3 dimensions. So there are 3n generalized coordinates and 3n generalized momenta, and therefore the phase space is 3n plus 3n equal to 6n. Suppose you are in 2 dimensions, then the number of generalized coordinates would be 2n, the number of generalized momenta would be 2n, and the dimension of the phase space would be 4n, and so on. Okay, in 1 dimension you would have a 2n dimensional phase space. Now, what is this phase space? It's a hypothetical space. It doesn't exist in nature. It's a space such that a microstate of the system, that is given set of values of the coordinates and the momenta, are represented by a single point in this high dimensional space. And then we talked about phase space trajectories, that is, each phase space point evolves in time following the Hamilton equations of motion, and a phase space trajectory doesn't self intersect. It can just wander around or it can undergo a periodic motion, but it cannot self intersect. Then we talked about ensemble, that is, given a macro state, I make a list of all possible microstates which are consistent with the given macro state, and list of all possible microstates or collection of all possible microstates consistent with the given macro state has got a name, and this name is ensemble. And in the next class, we are going to take up the concept of phase space density, and then there is something called Liouville's theorem. And gradually, we will develop this alternative view of understanding, uh, the question or answering the question that we set out to answer, namely, what would be the state of my iPad 5 years down the line? Okay. Fine. Is this okay to everyone? Please try to answer this question on your own. And after you yourself have found the answer to this question, then you can consult your friend and find out, whether you have found the same answer and so on. But please try to, it's not a mathematical question. It has more to do with conceptual understanding and some commonsensical view of the world. Try to answer this question, and then we'll take up in the next class the topic of phase space density and Liouville theorem and so on.
Hello,
Okay.
sir.
Yeah.
Sir, please repeat the question.
I have already written it.
Sir, I cannot understand the question. Please say again.
So in the phase space, suppose there is a microstate and this is the phase space trajectory. Suppose there is another microstate and this is the phase space trajectory. I am asking, can there be an intersection? Intersection, you understand?
Sir.
So I am asking if the phase space trajectory corresponding to microstate 1 and corresponding to microstate 2, if these two phase space trajectories can cut each other.
Okay, sir. But sir, phase space has 6 n dimension.
Yeah,
so it has only one trajectory. If you say for every particle there is a trajectory in phase space.
No, now you need to view the lecture once more. Okay? Because I told you several times that there is for every particle, every microscale, this one, this point, it corresponds to 6n values. What do you mean by every particle, right? That's what I said, no? A microstate is a point here. This is a microstate of the system. This contains the coordinates and momenta values of all the particles. This contains the coordinates and momenta values of all the particles. And this is a line. This is one line and that is another line. And I'm asking whether two lines can cut each other, cut each other or not. Okay. The particle concept is not there because it's a 6n dimensional space. The particle concept we have already gotten rid of. We are talking in terms of microstates, not in terms of particles. These microstates, it's not that this is particle number 1 and this is particle number 2. This is microstate 1 and this is microstate 2.
Okay, sir. Okay, sir.
Okay, particle to yeah, na? Okay. Please view this lecture because that's one advantage with this online thing that you can view the lecture once, twice, thrice, as long as you have the energy and patience. Try to understand things and try to go over the parts where I explain this. This is not particle 1, particle 2. Yeah, because a particle 1 would need 6 coordinates. Sorry, 6 values. 3 coordinates and 3 momenta. It would not need 6n values. So this point, it corresponds to all the particles. This point, it corresponds to all the particles, right? For the entire system, right? Okay.
Sir, will you give us any notes or something as you give in
No,
same one?
I don't think. I don't think, because I don't have any notes prepared. I think the lectures, if you know, whatever I write here, I mean, you take them as my notes. I'm doing everything from my mind. I'm not, although I said Carson Wang and all, but I've been, I fell in love with statistical physics from 20 years ago, and I'm still with that subject. So I more or less now know all these things by heart. So you take this one as my notes, so everything is there. Like, I mean, in the if you want, do you want this, what you call the um,
Yeah,
this
maybe they want this set. I mean, whatever you're writing.
convert it into a PDF, so that I can do. I can convert this notebook into a PDF and send it over to you. That's what you want, right?
Okay, sir. Okay.
Okay. Okay. Fine. Okay then. So let's call it a day. Thank you very much, and then we'll meet again on next Wednesday at what's the time? 12:30. Okay.
Bye. Bye.
Okay then. Bye. Yeah. Thank you.